Okay, you guys, we are now about halfway through the semester, or a little thereafter, and we are getting into Lecture 8 on plate tectonics. The theory of plate tectonics describes the highly evidenced idea that our outermost layer of the Earth is broken into different pieces or plates that move about the surface of the Earth, bumping into each other, moving away from each other, sliding past each other, having different interactions which control major geologic events. These plates move relatively slowly with respect to a human lifespan, on the order of about 2 centimeters per year for average across the globe. However, with the consideration of geologic time, that's actually a rather rapid rate. Tectonic plates are comprised of the lithosphere. So if you'll recall from earlier in the semester, that is the portion of the Earth, the outermost portion, that is brittle in nature. So that is both the oceanic crust and the continental crust, as well as the uppermost mantle. Directly below that is the asthenosphere. That is a soft solid, which is what allows those tectonic plates to be mobile. Earth is unique in a lot of ways, and one of those being that it is the only known planet with tectonic plates. There is some evidence that one of Jupiter's moons, Europa, might have some tectonic plate activity. However, it's inconclusive at the moment. So because of plate tectonics, Earth's surface looks quite different from other planets. Number one, we have an ocean. We have unique temperature and moisture conditions here on Earth that allows us to have an atmosphere and keep our oceans, at least for the time being. Recall that during our geologic time lecture, you saw that there has only been an ocean on Earth for, for about 3.5 billion years. And then Earth actually has continents, whereas other planets in our solar system do not. And this is because of the interaction of different plates. All of these major topographic features, mountains, trenches, ridges, so on, are all because of the interaction of tectonic plates. Pushing plates together and building up mountains, or stretching them apart and forming trenches or ridges. These high highs and low lows only come from tectonic plate interaction, which is why other planets do not have continents. There are several lines of evidence for plate tectonics that we'll be going over in this lecture, one of which is that our continents themselves fit together quite nicely if arranged like puzzle pieces. The connection of all of these continents together with one major continent rather than the several we have today is referred to as Pangea. The world looked like this some 200 million years ago, and there have been several names for the different continents as they have drifted apart at different points in time, and this is because of continental drift, or the movement of those tectonic plates. So I want to show you guys real quick this interactive viewer. It's by BioInteractive. You guys can find this online as well. The link's up here. And this is an interactive map that shows the migration of continents through time. So it's nice because it's three-dimensional, and this should look fairly familiar. This is current day. If you come over here to the left-hand side, you can see our time scale. So we can move backwards in time to, say, the Jurassic. Everybody likes the Jurassic because of Jurassic Park. And we can see exactly how the continents fit together at that point in time. Another neat feature of this is that you can also see what the atmosphere was like in terms of oxygen concentrations and carbon dioxide concentrations at that point in time. ppm is parts per million, and then oxygen here is in percent. This is important to pay attention to because these two atmospheric components are the most critical for life. Note that if we bring this back up to current day, our oxygen is at 21% with a 392 parts per million carbon dioxide concentration. And the neat thing about this is that as you drag this through time, you can actually see where those levels spiked, and they overlap with several mass extinction events. Notice over here in the right-hand corner as well that the length of days have extended through time and changed through time. So here in the Jurassic, we're at days that are about 23.2 hours in length. Of course, current day we're at 24.0, but say back in the Carboniferous, or the Devonian, or the Silurian, lower and lower numbers for the number of hours per day. And this is because the rate at which the Earth actually rotates has slowed down over its period of existence. Now, mind you, this is not because of it losing momentum, because if things are sent with a certain velocity in space, they will maintain that velocity. Newton's laws state that objects in motion will stay in motion unless acted upon by an outside force. That outside force here on Earth, usually being gravity or friction, air resistance, so on and so forth, none of which exist in space. So if that were the case, the Earth would just continuously spin or rotate at the same rate. This slowing is actually due to the expansion of our universe on whole. So our moon is now further away from Earth than it once was, and it's continuously moving further and further away, which means that it has a lesser gravitational effect on the Earth, because an increase in distance equals a lesser gravitational effect. If things are closer to each other, their gravities will have a greater effect on each other. And as the moon moves further and further away, the Earth's rotation will continue to slow. So the default setting for this is in the Paleo-Earth, which means that we're going from the Paleozoic to the Cenozoic, but you can look at different periods, such as Ancient Earth if you want to go further back. We can drag this all the way down to the Paleo-Archean, and you can see that Earth looked really quite different. No Arctic poles, hardly any continents at all, very minimal. On the other hand, we can go all the way up to the Ice Age, zoom in on that specifically, where we can see ice coverage not as major as some people may think. And we can go to current day, or warming Earth. This is actually only to 2012, but we can see the difference in temperatures throughout the Earth. Now, mind you, this temperature range isn't purely the temperature itself, otherwise we would see the hotter temperatures, the reds, towards the equator, right? But rather, this is the change in temperature from 1912 to 2012. So in the last about 100 years, how much temperature has changed on the order of degrees Celsius. So we've seen the greatest change in North America, northern North America, and into the North Pole, as well as a few other particular areas, but generally closer to the poles. It's where we're seeing the most dramatic changes, whether that's an increase or a decrease. So this is a highly interactive tool, a lot of fun stuff to play around with on this. I encourage you guys to take a look at it, especially the feature for moving through the Paleo-Earth history. You guys can really see a strong visual on how continents have moved over time, and even down to Pangea. Well, not quite there. But you can move closer and closer to it and see just how dramatically things have changed over Earth's rich history. And if we were to zoom in on a bunch of specific spots within that rearrangement, we would notice that there are several mountain belts that match up between several continents. So we can take the Appalachian Mountains in the US and the Caledonian Mountains of Europe, and when these are fit together around Greenland, they form a perfect arc, matching up perfectly. And that's just one of several examples. The same pattern continues when we have all of the continents smushed together into Pangea, When we're considering past climates or depositional environments, those line up near perfectly along boundaries for that age range around 200 million years ago, where we can see that these depositional environments clearly stretched between the two continents, and they must have been together geographically at that point in time. But as you guys have seen in our previous lectures in labs with sedimentary rocks, there are a number of depositional environments that can create similar products in terms of rounding, sorting, and composition. So one of the more compelling pieces of evidence in this same regard, with all of the continents fitting together, is the fossil content. There are a number of since long extinct beings whose fossils we can see occurring in geographic bands across the connected continents of Pangaea, both living mammal type creatures and several different types of plants. And for the ones that were terrestrial based mammals and reptiles and so forth, we can actually see their literal footpaths going from one continent to another. And that was the only way that they were able to travel at that point in time, so we know that there must have been, at the very least, a land bridge shallow enough for them to walk across. Right? These guys aren't flying business class. Back in the early 1900s, there was a scientist named Alfred Wegener who originally proposed the idea of continental drift to explain these observations and relationships between the continents and their connections. However, this was only to the extent that he thought continents were moving and that they had once been together. As far as the ocean went, no idea. Continents could potentially just be floating on top of the ocean. Don't know. It's just about the continents moving. Of course, with this point in human history, his ideas were not very popular. This was during a time of very strong religious roots in government, and it was not aligning with the ideas of the religion that Alfred's country belonged to. But in arguing this idea, there were very valid questions that came along, such as how are entire continents moving? What is the force behind this? What could possibly be strong enough to do that? And then, well, if we know that the ocean ends at some point and then there's rock, how is rock going to move on top of rock? That just doesn't work. Well, we now have some answers for those questions. But between Alfred Wegener's point in time and today, where we have some answers to those questions, there have been several developments and other pieces of evidence gathered to support the theory of plate tectonics. One of those being the magnetic orientation of minerals within rocks. If you guys think back to your minerals lab, you'll recall that some minerals have magnetic properties. Many of these show up in igneous rocks, so anything coming from volcanic activity. And as these are being generated, those magnetic minerals will orient themselves within the rock towards the magnetic poles of the Earth. Now, we've discussed briefly before that Earth's magnetic poles change through time. Notice here in this diagram that we have a geographic north, that's the black line going through the Earth in this diagram, and then the magnetic north. And they do not line up. That's because they're different, and magnetic poles continue to change through time. In simple terms, this will basically rotate, making a full 180-degree change over the course of somewhere between 200,000 and 300,000 years. And because we have rocks that are much older than that, we can see that change in magnetic alignment through time. So these magnetic orientations help us decipher both when the continents were moving and in what direction they were moving. So at points where you have new rock created, major ridges where you have a bunch of new magma upwelling, you can see that each time that there is an eruption, it pushes out what was there before, because that new magma is going to make space for itself. So it's pushing whatever was there on top of it on either side before further and further out, and each of those increments will have slightly different magnetic orientations. So we can see by analyzing the magnetic orientations on either side of that magmatic intrusion, which way the continental plates were moving. The 1980s may seem like forever ago to some of you, but in terms of major scientific developments, or specifically in geology, the 1980s was essentially yesterday, which was when the theory of plate tectonics became popularized. Alfred Wegener was certainly not around to see this happen. And this was a completely revolutionary idea for the time. If you today went up to a professional career geologist in the 1960s and tried to explain the theory of plate tectonics to them, chances are they would probably recommend that you take a sticky sock vacation. But today, with the advancements of seismic technology and volcano monitoring, we now have an overwhelming amount of evidence pointing to the validity of plate tectonics. We also now have a much better idea as to the driving force of plate tectonics because of seismic surveys and being able to see from essentially one side of the Earth all the way to the other using the properties of P waves and S waves. The prevailing hypothesis for the driver of plate tectonics is convection currents taking place in the mantle. We talked about this back in the second week of class with the interior of the Earth. If you guys remember the conversation about convection ovens and how there's a heating element and heat will rise and then it will fall and then it will reheat, rise, cool, fall, reheat, rise, cool, fall, over and over again, developing these convection currents. It's the same thing in your oven as it is in the mantle. When you consider it in its simplest terms. And we can verify this by evaluating the velocity of P waves and S waves through this material and see that it actually changes with changes in temperature, and so as well as changes in density, so we can actually map out these exact convection currents. The uncertainty with this hypothesis comes down to what degree is the actual movement of the plates perpetuating these cycles. So if we have plates that are moving outwards, wouldn't they to some degree push these upper convection currents along until it comes down? And if this plate is subducting here and this is coming down here, isn't that not too pushing that convection current along? To what degree, we don't know. We also don't know which came first, the movement of the plates or the convection currents themselves. It's a classic chicken or the egg conundrum. And depending on what geophysicist you talk to, you may get a different answer. But a couple more vocabulary terms for you guys real quick. When we have the magma moving up towards the surface of the Earth, we call that upwelling. It's moving up. That's because it's hot and it's more buoyant. It's less dense. It'll continue to move up. And then downwelling is when it cools down, it becomes denser, and it sinks back down to the core, where it'll be reheated and pushed back up. So this cycle of upwelling and downwelling. Per usual, I've included a good point here for you to pause and take a quick brain break before getting back into it, which we'll do in a second here. Moving on. There are several different types of plate boundaries. A boundary being a place where any two tectonic plates meet. And there are several different types of these. They are categorized by the direction of movement of the two plates involved at that spot. So number one, we can have a divergent plate boundary. This is when plates are diverging from one another. If you guys think back to our metamorphic rocks, there are several different types of stresses that a metamorphic rock can experience. One of those being tensional, that's the stretching or pulling apart. So that you can think of it this way, is that this is essentially a large, very large scale version of that same idea. When we have this tensional force between two plates, moving apart from one another, we will end up with a process called rifting. So this develops by first forming a rift valley, if this is in continental crust, where this tension will continue to thin out the rock in between them until it's no longer there. And then because this is then a low topographic point, it will naturally accumulate loose sediment and water and often become a rift valley filled with a river or loose stream, just depending on where it is topographically in the first place. Fast forward a number of tens of thousands of years, we'll then have this rift valley within an ocean, which is creating new crust, new oceanic crust. And you guys can see these little lines or separations. That's exactly what I was referring to earlier with the magnetism, is that every time this magma pushes its way out, it makes space for itself. It's pushing out layers on opposite sides, continuing to push these two plates away from each other and creating new magma in the center. This is called seafloor spreading, where you'll see the newest magma at that rift and the oldest rock farthest away from that rift. On the opposite side of a diverging plate boundary, we will often find a converging plate boundary. Converging meaning they converge or come together, so they're pushing together. This is comparable to the compressional stress exerted on metamorphic rocks. Hopefully you guys remember from one of our earliest labs that oceanic crust is more dense than continental crust. And when it comes to density, that is what dictates whether something will rise or sink. Anything that's more dense will sink than its less dense counterpart. So with oceanic crust being more dense than continental, if they collide or converge, the oceanic crust will subduct or go underneath the continental crust, as pictured here. If you guys remember from the volcanism lecture, there's this component called, or this process called, flux melting. Because this oceanic crust has some degree of water content because of the ocean, that actually lowers the melting point of the rock, which means that it can start to melt at relatively low depths. This magma will then become less dense from its solid state to its liquid phase and will begin to rise, which is why we oftentimes end up with a series of volcanoes on the interior of a continent just off the coast of a subduction zone. So these plate tectonic movements are really the control on these major geologic features, such as a volcanic arc or line of volcanoes. And mind you, this is a three-dimensional feature. The plate is going down all the way underneath here, so that's why you end up with a series of volcanoes or volcanic arc. And then at this actual subduction, this is a really deep but thin trench right in between these two plates. It goes all the way down to where that plate is actually subducting underneath one another. And because this is sort of peeling both of them down a bit at the top here, that becomes quite deep, forming a trench. So again, these major geologic features are all connected to the movement of tectonic plates. And here's where you can furthermore really see the connection between those convection cells and the movement of the tectonic plates. Consider the upwelling, right? Where it's upwelling or moving up, that's where we're going to end up with a split in the surface and getting some new magma. And anything that doesn't fit through that tiny crack is going to end up moving back over and cooling towards the crust, pulling this plate while the plate is also in part pushing it along, and then sinking back down with that plate, eventually getting reheated. It's downwelling at this point, getting reheated, and then back again to upwelling, perpetuating this cycle of movement, as well as construction and destruction of major topographic features. So seafloor spreading is really the major constituent of motion of the plates. Really, even though this is pulling two plates apart, it's really due to a pushing, because that new magma is coming in and pushing them away from each other. So Don't get too confused. This is still tensional, it's still diverging, but know that the main mechanism of all of this movement is magma upwelling and pushing things around. And know that if it's pushing up and diverging at one part, on the opposite end, it's converging and sinking via subduction. So it all ties into one another. So circling back again to the stresses on metamorphic rocks, you guys remember that there was tensional, which on large scale with tectonic plates is divergent, and then compressional, comparable to convergent boundaries, and then there was also shear or frictional stress, which in terms of plate tectonics, large scale is referred to as transform. It's a transform boundary. And these are when two tectonic plates are sliding past each other. For the most part, this occurs along other plate boundaries, so it'll be small portions of what are, for the most part, convergent or divergent, where you'll find little portions that are transform. There's often a lot of faulting related to divergent and transform boundaries. Those are our sort of destructive boundary types, whereas convergent is more constructive. So if you have convergence, it's usually going to develop topographic highs. As that oceanic plate slams into the continental, the oceanic subducts, but the continental is being pushed up against and will rise in height, creating and building mountains. For transform and divergent, these are more destructive and will usually have faults or breakages, three-dimensional breakages along the surface of those plates. So to give you a better view of faults, it's when we have these two pieces that are going to, were previously one piece, broken into two, and then have moved in some way, shape, or form. Usually we see this in the form of normal faults. So in any fault, there is a footwall and a hanging wall. So it's one piece and another piece. A good way to remember which is that the footwall is the part that has a slope that you could put your feet on and walk up. The hanging wall, however, you couldn't walk along this slope here. You would have to hang from it and climb up it. When a hanging wall is below a footwall, so the surface of that hanging wall is below the surface of the footwall, it is a normal fault. Because when you pull apart and break rock, it will normally slide in that fashion. We see a lot of these in rift valleys. Remember in that earlier figure where we had the two plates diverging and pulling apart, and it got thinner and thinner in that portion in the middle? Well, as it gets thinner, this rock is going to become more and more fragile and broken up, and it's going to be lined top to bottom with faults. Our major global ridges are referred to, or rifts are referred to as mid-ocean ridges. This is where if you're looking at a seafloor spreading map and it looks like a big thick red line all the way through the middle, like what you're seeing in lab this week, that's a mid-ocean ridge. There is one, the Mid-Atlantic Ridge, that goes directly through Iceland, which is the reason why Iceland has such a high degree of volcanic activity. And all of the major volcanoes in Iceland actually sit right along that ocean ridge, as marked by these triangles here. There's actually a tourist spot in Iceland where you can metaphorically stand on the mid-ocean ridge there. Really, it is on top of the mid-ocean ridge, but it's a rift valley on top of the mid-ocean ridge. So it's much smaller and it's highly faulted rock, and there's a river flowing through it. But that's only a rift that's maybe 50 to 80 feet across, but this mid-oceanic ridge here is on the order of several miles in width through Iceland. but it's still fun and cool. And then we have fissure volcanoes. Recall from the volcanism lecture that these are essentially large to us, but not large in comparison to mid-oceanic ridges, cracks in the earth where you have a long linear feature where magma is upwelling. For convergent plate boundaries, the major features associated with this are trenches and mountains. So where these two plates collide, we'll have that trench, that deep point right where they're both sort of sinking in, mostly the oceanic plate, but this one as well. And then because of that crunching or pushing together, we've got some mountain building right next to it. So a high followed by a low, or a low followed by a high, depending on if you're reading left to right or right to left. This is what happens when we have an oceanic plate, a plate which is mostly ocean, converging with a continental plate, a plate which is mostly continent, or when we have oceanic meeting oceanic. However, when we have continental meeting continental, happens less commonly, but it's still possible, and we have several examples of it around the world. We don't end up with a trench, but rather a much wider stretch of a mountainous region because there's less dispersion of that stress. When these collide, a good deal of that stress is in the subduction action, so the reverberated stress is what builds these mountains. If there's no subducting plate, then all of that stress goes into the direct collision, so we end up with a lot wider mountain plane with our highest mountains right at the collision site, and then gradually lower or shorter mountains further and further away. So, quick review, 3 types of convergent boundaries. Type 1, when an oceanic plate collides with a continental plate. The continental plate will be less dense, and then which will result in a subduction zone with the oceanic plate subducting underneath the continental. Gives you a trench and some mountains. Again, likely going to have a number of inland volcanoes in a linear pattern along the interior of the continental plate due to the flux melting associated with that subduction. The Andes Mountains in South America are just one of several examples of where subduction or collision of an oceanic and continental plate in that subduction has resulted in mountain building. Type 2, oceanic and oceanic plate converging. Essentially the same idea, but there's less significant mountain building, and part of that is just because, number 1, the 2 plates are thinner. Remember that oceanic crust is thinner than continental crust. And 2, that there's a lot more elevation change to cover in order to build the same kind of mountain because you're starting below sea level in this case. And then type 3, where things get a little more interesting, with the convergence of 2 continental plates, you're going to end up with a whole lot of faulting and folding, which is going to produce a graded mountain range in terms of height, with the highest mountains right at that boundary and smaller further away. Both the Himalayas and the Rocky Mountains are examples of a result of this tectonic interaction. Though less common, we can also get some faulting with convergent boundaries, and in this case we end up with a reverse fault. And this is because we're pushing these 2 blocks together. Same thing again, a foot wall where you could put your feet on it and walk up it. This slope right here. And then a hanging wall where you could not walk up this slope, you'd have to hang down from it. And a reverse fault, we have the surface of the hanging block above the surface of the footwall block. One tricky thing with transform boundaries is that if they're a small enough scale, they're often referred to as transform faults. These are often used interchangeably, and there's a whole lot of gray area between referring to a transform plate boundary and a transform fault. Often that transform fault is a portion of a plate boundary where the rest of it is either convergent or divergent. In either case, it's where we have two plates sliding past each other rather than coming together or moving apart. This interaction can also produce a lot of destruction. However, we're not losing any rock in this case. It's not subducting, nothing's melting away. It's just sliding past each other and breaking up into pieces. The San Andreas Fault in California is actually a classic example of a transform fault. The western portion of California is actually moving upwards while the eastern portion is moving downwards. So these two massive portions of rock are sliding past each other, and if you guys have been watching the news at all in the last several decades, you may have heard about a series of violent earthquakes associated with this fault specifically. That's because that's a lot of earth to be moving and to be interacting. That produces a number of earthquakes and or large vibrations essentially, as well as smaller faults along this larger fault, which can then later down the line cause a host of other problems like rock falls or sinkholes and other small scale features. We'll get more into the details of that in a later lecture on natural hazards. If you haven't seen it before, this is an aerial view of the San Andreas Fault where you can quite literally see that gap where these two chunks of rock are moving past each other. And all of these linear parallel features that you see formed, those are all faults, are what you're seeing. And oftentimes we see it in that pattern, in this linear, very straight, and elongated to a very similar distance, as well as parallel. And that's because it's trying to relieve stress in that direction. So that stress that it's relieving will always form perpendicular to that direction. So here's your major fault. This is the direction of stress. And so these faults will form perpendicular to that. This kind of interaction gives us our final type of faulting. And in this case, we have no hanging wall, we have no footwall. There's no slope between these two, they're just flat faces, or relatively flat faces, and they're moving past one another. There's no compression, there's no tension, it's just sliding past one another. So we call this the strike-slip fault. And this is associated with transform faults, or transform plate boundaries. Okay, a lot of new information for you guys, a lot of new vocab terms. Again, this is a good point to hit pause and take a quick break, highlight some terms, and then come back to it. Okay, now we're gonna take a step back and zoom out a bit and look at this from a global, big picture perspective. As we've seen, the motion and interaction of tectonic plates are the primary control on major geologic events and topographic features on Earth's surface. When they pieced together the actual location of these boundaries, it was in part because of those topographic features, but in majority because of a number of data sets that we had. Those being volcanic activity, seismic activity or earthquakes, seafloor spreading, and then of course the topography itself. The plates generally line up with the edges of continents, such as along North America here, as well as South America, and along the islands, Papua New Guinea and Indonesia, as well as fitting around Arabia, so on and so forth. There are certainly exceptions to this rule, such as Australia and Africa, India kind of as well, where these actually do line up with other topographic features such as the Himalayan mountain belt along this border of India for continental to continental collision. This is the Indian plate and the Eurasian plate. But point being, you can't build a tectonic plate map off of purely that. So we can also consider the age of the seafloor. These are points where we have actually been able to go out and collect seafloor samples and conduct age dating analysis on them and figure out how old they are, as well as see their magnetic orientations. Those along the red are the newest magma, which happen to align directly with our divergent boundaries, right? And then as we get further and further away, we move into the cooler colors, which align with the older seafloor ages. This for us is a very strong confirmation of the location and existence of divergent plate boundaries, specifically mid-oceanic ridges and oceanic divergent boundaries. For seismic data, we see the same idea that the occurrence of earthquakes, all of these little black dots here, are following the lines of the plate boundaries, which makes sense because that's where they're colliding or sliding past each other or diverging. We tend to have the highest density and strength of earthquakes at convergent plate boundaries because they're slamming up into each other. Transform is a short second to that because they're sliding past each other. Where we have the least are along divergent boundaries. Notice that we have a much lower density of dots or earthquakes here along that mid-oceanic ridge, right? And then we can also consider the depths of their occurrence. So because oceanic crust is thinner than continental crust, we usually see earthquakes occurring deeper in oceanic crust than we do in continental crust. And then, of course, everyone's favorite, Johnny Cash's The Ring of Fire, is the arrangement of volcanic activity relative to these boundaries. Now, this, as we've seen, can be indicative of both divergent and convergent, depending on if it's right at that divergent margin or it's a little bit inland of that subducting convergent margin. But we can see those reign true when we look at the distribution of volcanoes. Remember, we have this transform, but also cut out a little bit there, but we have here for the Cascade Mountain Range, the mixture of the transform fault as well as a convergent or transform boundary as well as a convergent boundary. So we have this series or linear distribution, right? It follows itself in a line along that edge of the continent. So it follows that edge of the continent because that plate is subducting there, and we have some flux melting creating some volcanic activity in this range. You can see that here in South America as well. See it a little bit even further inland on Africa, and continuous across many other places on the globe. But when we consider divergent areas, we see a high density of volcanoes occurring right along that divergence. And that, of course, is because that is directly where magma is upwelling. Take, for instance, Iceland again. We see all of this volcanic activity in Iceland because it's sitting right on top of that divergent boundary. And of course you can say, well, what about these random spots all over the place that don't seem to have quite anything to do with any of the plate boundaries? And those are hot spots. If you guys remember, we talked about Hawaii a little bit. That's a classic example of a hot spot, but those are just somewhat random points on in the Earth's crust where it's much thinner, and we have a little localized point of upwelling magma. Now, these are not clearly, at least not currently clearly tied to plate tectonics. We're not completely sure on what the mechanism is. We just know that it's thinner, the crust being thinner at those locations. Though there is notably some correlation between areas with volcanic arcs and hotspots. such as Yellowstone. There's a couple of hot spots somewhat around this area, as well as Iceland. There's a hot spot there, and on the far east side of Africa, some hot spots along there that sort of follow that linear feature, linear distribution of volcanoes from that subduction as well. So this is something that geologists are actively investigating. In any case, one thing to notice between all of these data sets that we're considering is they all point to the existence of tectonic plates, those interactions that they have. This is all very strong evidence for this theory, which is why it relatively quickly morphed into, from a hypothesis into a theory supported by an overwhelming amount of data and testing. Okay, couple of take-home messages for you guys. Remember, Earth's geology is dominated by the processes of plate tectonics. This only happens on Earth, except maybe one of Jupiter's moons, though we don't really know that completely for sure. But it is pretty well unique to Earth. Earth's crust and upper mantle are divided into plates, so the whole lithosphere, it's not just the crust. Plate movement is driven by convection in the Earth's mantle. It's that upwelling and downwelling. We don't know what degree they're perpetuating each other, but they are intrinsically linked. Crust is continuously being regenerated and removed. So at the divergent margins, we have new crust coming up and being formed, and then on the opposite end, where it's subducting, we have it being destroyed or removed. It's more so reintroduced to the mantle rather than removed entirely. It doesn't just disappear. Where plates interact, that often forms earthquakes, volcanoes, and mountains, trenches. These are where we're getting our major features and events. Things get a bit more boring or a bit more safe, depending on how you want to look at it, closer and closer to the interior of plates. Okay, finally, a few last reminders for you guys. Take the lecture quiz, finalize your topographic map lab, and complete the plate tectonics infographic activity. There's information on this in the module. You've got a couple weeks to do it. But it's a little bit of investigation, a little bit of creativity. Feel free to have some fun with it. All right. Hope you guys have a good week. I'll talk to you next time around.